All right, today let's take a look at a few more motion problems. Now, this first box that's on your note sheet is a lot of the information we've talked about already. All right, so displacement, we talked about that idea already. It's the total change in position. Right? So it's not total distance traveled, okay? It's just change in position relative to where you started. Um, Average velocity, okay? This is actually kind of a new idea, right? We've talked about average rate of change. Right? Remember, average rate of change just meant slope, slope between 2 points. Right? Instantaneous rate of change was slope at a single point. Average rate of change was slope between 2 points. Same idea with velocity. Instantaneous rate of change of velocity is our derivative of position. Average velocity is just the slope between 2 points on my position curve. Right? So we could say that's displacement divided by the time. So if we see average velocity or average rate of change, all we want to do is take the slope between the 2 points in question. Similarly, well, first, just a reminder, we'll look at this a little more today. Speed is the absolute value of velocity. So then similarly, average acceleration is the change in velocity over a period of time. Right? It's the slope between 2 points on the velocity curve. So if we see average acceleration, we need to find 2 points, or the 2 points in question on our velocity curve, and find the slope between them. Okay, those are really the only two new ideas in that first box there. Okay, so let's jump into a problem. Right? This first problem down at the bottom says, to save his son, Luke Skywalker, from certain death, Darth Vader picks up the Emperor and throws him off of a ledge on the Death Star. As he falls, the Emperor's position is given by the function s of t equals negative 16t squared plus 16t plus 320, where s is measured in feet and t is measured in seconds. All right, so let's actually take a look at this function here. All right, if we plot this function, and again, I'm just starting at 0 because we're saying t starts at 0. The Emperor is thrown off, and this is his position, right? This is not an actual picture of the path that he takes. This is his position in the air with respect to time. Okay, so we know initially he's at 320 feet, right? And then Darth Vader actually throws him up a little bit. Okay, he goes up just a little bit and then comes down to the ground. So let's take a look at these questions to analyze this function. So first, we want to know the Emperor's displacement from t equals 1 to t equals 2. So what we need to find is s of 2 and s of 1. Right? So if I plug 2 into this function, actually, we could do this by hand or on the calculator, but let me just go to the graph here. So at 2, our function value is 288. All right. So s of 2 is 288. And if I go back and I need s of 1, so s of 1 is 320. And again, we could do that by hand. Right? I could plug 1 into this function and get 320. So my displacement then is my final position minus initial position. So in this case, my final position is at 2 seconds, and my initial position is at 1 second. So 288 minus 320 gets me a displacement of negative 32 feet. So what we're saying is on this interval from 1 second to 2 seconds, the Emperor has fallen 32 feet. All right. Let's Let's take a look at B. When will the emperor hit the ground? All right, so we want to think about the emperor's position when he hits the ground. His position would be 0 when he hits the ground, right? So what I want to do is say my position is equal to 0. Okay, I want to say 0 equals negative 16t squared plus 16t plus 320. Now I just have a quadratic that I want to solve. Right? So let's see, I could divide everything by negative 16. So if I do that, let's see, we would get t squared minus t minus 20. So now, let's see, does this factor? I think it does. Right? If we factor this, let's see, two numbers that multiply to negative 20 that add to negative 1, we would have t minus 5 and t plus 4. So setting both of those equal to 0, we would get t equals 5 and t equals negative 4. But since we're talking about time, negative 4 seconds doesn't really make sense, right? So what we would say is after 5 seconds is when the emperor hits the ground. And again, we can see that on the graph, right? At 5 seconds is when his position is now equal to 0. Right? So we start at a height of 320, and the emperor gets thrown up just a little bit and then comes crashing down to the ground. All right, let's take a look at C. So C, what is the emperor's velocity at impact? All right. Well, we just said this impact occurs at 5 seconds, right? Well, how do I find the velocity then at 5 seconds? Well, we know velocity is just the derivative of position. So my velocity function, if I take the derivative here, would be, let's see, negative 32t plus 16. So if I plug 5 in, v of 5 will be negative 32 times 5 plus 16. So what do we get? Negative 32 times 5 is negative 160 plus 16 gets me negative 144. So his velocity at the time of impact was negative 144 feet per second. Now we want to know the speed at impact. Well, speed, we know, is just equal to the absolute value of velocity. So the emperor's speed at impact, so we can say speed at t equals 5 is equal to the absolute value of v of 5, which we know is negative 144. So the absolute value of negative 144 is positive 144 feet per second. All right, remember, this negative just tells me the direction. Okay, this means the emperor was going down. Right? Speed is directionless. Right? That's why speed is always positive. This positive or negative in velocity just gives me a direction. All right? And the last part here on this question, find the emperor's acceleration as a function of time. So this is just saying, give me a function, right? So I need the second derivative. We already said that velocity was equal to negative 32t plus 16. So then my acceleration, if I take the derivative of velocity, is just going to be negative 32. Right? So that would actually be negative 32 feet squared per second. And notice this is our constant of acceleration on Earth. Right? Acceleration is negative 32 feet squared per second. All right, this one, okay, I want you guys to take a second and find the velocity and acceleration for this graph. All right, so velocity, right, or instantaneous velocity at any time t just means find the derivative of position. So velocity is going to be equal to negative 3t squared plus 24t minus 15. All right, and find the acceleration of the particle at any time t. Well, I'm just going to take the derivative here. So my acceleration is negative 6t plus 24. Okay. So now, part C says, when is the particle at rest? We talked about this yesterday. Okay, remember, particle at rest means that our velocity is equal to 0. So take a second and see if you can solve this. Okay, it won't be a nice number, I'll tell you that much. All right, so my velocity function, we said, was negative 3t squared plus 24t minus 15. Right? So velocity is negative 3t squared, I forgot it already, plus 24t minus 15. So I just want to set this equal to 0. So 0 equals negative 3t squared plus 24t minus 15. It looks like I could divide everything by negative 3. So if I do that, I would get t squared minus 8t plus 5. Now, this will not factor, right? There are no numbers that multiply to positive 5 that add to negative 8. So if we wanted to do this by hand, we would need to use the quadratic formula. So I can say x equals opposite of b, which would be positive 8, plus or minus the square root of b squared, so negative 8 squared, minus 4 times a times c, all over 2 times a. So if we simplify, we get x equals 8 plus or minus the square root of 64 minus 20, so 44 over 2. Let's see, I could simplify this a little bit more and say 8 plus or minus, this would be 4 times 11, so I could make this 2 radical 11 over 2, and then that would simplify, if I divide everything by 2, to just 4 plus or minus the square root of 11. So if I wanted exact answers, that would be what I would say. And I guess I should have actually made this t, not x, right? So these are the times when the particle is at rest. 4 plus or minus the square root of 11. Now, if we want a decimal, let's see, what is 4 minus the square root of 11 is 0.683. So 0.683, and 4 plus the square root of 11, 7.317. So those are the times, okay, after 0.683 seconds and after 7.317 seconds when my velocity is 0. Okay, now this last part, part D, describing the entire motion of the particle. Okay, this one is a little bit weird to think about at first, okay, but just from looking at the graph, we can describe this particle's entire movement, okay, and we do want to do that by looking at the graph. All right, so I want you guys to take a second here and see if you can fill in these blanks, okay? I'm not going to put up questions, I just want you to pause the video for a second and think about these blanks, all right? And can look at the graph of this function as we do that. All right. Okay, so I guess I should have said x is greater than 0. All right, so here's my function, right? My position, okay, is I start out up here, right? All right, I start out actually at a position of 15, okay? I start out at a position of 15. That's my initial position, right? So the particle starts at s equals 15. Now, which direction does it move first? Well, my y value telling me my position is going down, right? This means that my particle moved to the left first. If we're thinking about this is just a particle, moving back and forth across the x-axis, its position is getting closer and closer to 0. That means we're moving to the left. Another way to think about that is here we have a negative slope. Negative slope of position means negative velocity, which means I'm moving to the left. So we would say it starts at a position of 15 and moves to the left until it changes direction, right? Well, it changes direction right here, okay, at 0.683. We already found that value, right? That was the first time when the velocity equals 0. And then my position at that point, okay, it says is at 10.034. So my position, 10.034, and we said that was at time 0.683 seconds. So then my particle starts moving to the right again, right? It starts getting further and further from a position of 0. So it's moving to the right for this whole piece right here. And again, we also know that because this slope of my position curve is positive. That means the velocity is positive. So it's moving to the right. So I can say it moves to the right until it changes direction again up here at this point. And again, this is a point that we already found. Okay, we found that here the velocity is also equal to 0. It changes direction here. It goes from a positive velocity to a negative velocity. And that happens at a position of 155.966. 155. What was it? 0.966. And that occurs at time 7.317 seconds. From there, the particle then, turns back around and moves to the left, right? And it keeps moving to the left indefinitely. Right? We know that because the slope of my position graph is negative, which means the velocity is negative. Okay. Now, let's analyze a different type of graph. Okay. Let's analyze a velocity graph. Right? Now this is important. We have to look at this a little bit differently than our position graph. All the same ideas that we've used still apply, but we have to pay attention to the fact that this is a velocity graph. All right? So we want to think about all those same ideas. Where velocity is positive, we're moving to the right. Where velocity is negative, we're moving to the left. Where velocity equals 0, we're stopped. All right? So let's analyze this graph and answer all these questions together. This is my velocity graph. So which way does the particle move first? Okay, we start here at a velocity of 0, and then my velocity is negative. If my velocity is negative, right, and now I'm not saying that because the slope of this graph is negative. I'm saying that because the actual function value, the y value of this graph is negative. That's how I know what direction I'm moving first. Okay, I'm moving to the left because I have a negative velocity. Now, we want to know when the particle stops. Well, if I'm thinking about velocity, the particle has a 0 velocity right there, right there, right there, and right there. If we're looking at a velocity graph, we want the places where we cross the x-axis. Okay, those are the places where velocity equals 0. So we can say at t equals 0, 2, that's not 2, that is 3. Can't count. So 0, 1, 2, 3, 4, 5, 6, 7, and 8, 9, 10. So 4 places where the particle stops, right? At 0, 3, 7, and 10. All right. Now, when does the particle change direction? Okay. Well, in order for it to change direction, we have to change from a positive to a negative velocity or a negative to a positive velocity. Okay, so the only places that could happen, okay, is when our velocity equals 0. Well, we had 4 places, right? Here, 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 and here. But there's actually only one of those where we change from a positive to a negative or negative to a positive. That happens right here. Right? So we're moving left, moving left, moving left. We stop, but then we keep moving left, keep moving left, keep moving left, keep moving left. And then here we change to a positive velocity. That means I stop and then start going to the right. Right, 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 right. And then I stop again. So the only place where my particle changes direction is at t equals 7. Now, we kind of just talked about this one. When is the particle moving to the left? Okay, well, it's moving to the left on this whole piece here because my velocity is negative for this whole piece. So I can actually say it's moving to the left between 0 and 7. Right? It's moving to the left over this whole interval. Now, if we wanted to get technical, we could exclude this point as well, because technically at 3, it's not moving to the left, it's stopped right here. Right? But on AP tests, they actually don't get that picky, which is kind of surprising. Right? So we could say that it's moving to the left on this entire interval. All right? Let's take a look at the next two. When is the particle moving to the right? Well, it's moving to the right when velocity is positive. So that would be on this entire interval from 7 to 10. All right? And I guess we should also practice writing this in interval notation. Right? So interval notation, we would just say from 7 to 10 like that. Now, when is the particle speeding up? Okay, this is a key one. Right? Speeding up and slowing down are questions that are asked very often, and we're going to revisit this here in the next couple of days. Right? But this is kind of our first taste. The particle is speeding up. Remember, when velocity and acceleration have the same sign. So if we think about that idea, okay, velocity is negative all the way down here. Well, acceleration is the slope of velocity. It's velocity's derivative. So what I want to look at on the graph here is where the acceleration, where the slope is negative, and the velocity is negative. So that would actually occur on this entire interval, right, from 0 to 1. Oops. 0 to 1. I guess I'll write it in interval notation as well. And then it actually occurs again over here from 3 to 4. Right? The slope is negative and the velocity is negative. Right? And we can look for places where those are both positive as well. So on this interval here, my velocity is positive and my acceleration is positive because the slope is positive. So that's from 7 to 9. Now, there's actually another way that we can do that from a graph, right? From a velocity graph. If I am moving away from the x-axis, then my speed is increasing, okay? My speed is increasing here because I'm moving away from the x-axis. Speed is increasing here because I'm moving away from the x-axis. Now, we can also look at this again when we actually graph the speed here later in the problem. All right. So now particle slowing down is just the exact opposite of that. The particle is slowing down when velocity and acceleration have negative signs. So that would be here, here, and here. Okay. Or we can say when our velocity is getting closer to 0. Right. So from oops, I really can't count. From 1 to 3. From, what is that, 3, 4, 5 to 7. And then again over here from 9 to 10. So 3 intervals where that happens. Now, when is the particle moving the fastest? Right, well, that's going to be where its speed is greatest, okay? Where the velocity is furthest from the x-axis or the t-axis. Well, that happens down here, okay? This is where the graph is furthest from the x-axis. That's where the speed would be the greatest. So that occurs on this entire second, right? So that's from 4 to 5 seconds. All right. Now, when is the particle moving at a constant speed? All right. So constant speed means the velocity is not changing. Okay, well, that occurs right here. Right? My velocity is constant right here on the same interval. We just said it had the greatest speed. So, from 4 to 5 seconds. All right. Now, let's take a look at graphing acceleration and then speed. So we know acceleration is the derivative of velocity. So all I want to do is graph the derivative of this function. These are all line segments, so I can get the slope of each of these pieces, right? From 0 to 1, this line segment has a slope of -1. So, let me actually change my line thickness just a little bit. All right, so from 0 to 1, the acceleration is -1. From 1 to 3, that line would have a slope of 1/2. Now, notice all of these, and that one kind of looks like a closed dot, but all of these should be open dots, because at each of these places we have a corner, right? At each of those, the derivative here would be undefined. Right? Then my next piece, so that should have gone from 1 to 3. There we go. So from 3 to 4 then, my slope is, what is that, -4. So I'm all the way down here. Then here, from 4 to 5, my slope is 0. So I will be right here. From 5, actually all the way up to 8, I have the same slope here. From 5 to 8, that's a slope of 2. So I'll come up here to 2. That's my slope. Then from 8 to 9, I have a slope of +1. And from 9 to 10, I have a slope of -3. So this would be the graph of my acceleration function. I'm just graphing the derivative of velocity. All right. Now, let's graph the speed. Remember, speed is the absolute value of velocity. So all I want to do is wherever I've got a negative value here, I want to make it positive. So what my speed is going to look like, I'm just taking any negative parts and flipping them over the x-axis. So my speed, let's see, let me come up here. Then we are constant. Then we come down to here. All right, so this would be the graph of speed. All I'm doing is taking any negative parts and making them positive. I'm not flipping the whole thing. Right? This part didn't change. All I'm doing is taking the negative parts and making them positive. So if we think then about greatest speed, or where speed is increasing, it's a little easier to see from this graph, right? Obviously, greatest speed is right here. Okay, we already said it was from 4 to 5. My speed is increasing then here, here, and here. My speed is decreasing here, here, and here. Okay? Now, I want you guys to take a minute and go through example 4 here. Right? So pause the video, try each of these questions. And this is the same thing. This is a velocity graph, right? Mapping the velocity of some particles. So try to answer these 7 questions. Okay, when does the particle attain its maximum speed? So remember, actually, I'll go ahead and sketch this speed graph real quick here. So my speed graph would look like this, right? I would come up here and then come down here like this. So this would be my speed graph, right? Just taking any negative parts of my velocity graph and reflecting them over the x-axis, making them positive. So my maximum speed would be here at 3 seconds. So notice it says when, not what, right? So when does this happen? That happens at 3 seconds, okay? All right, try number 2. For what interval is the speed increasing? So again, if we think about that graph we just drew, speed is increasing whenever we're moving away from the x-axis. And that only occurs right here, from 2 to 3 seconds. So I could write it like this, or we could write it in interval notation. Okay? All right, try number 3. For what interval is the acceleration positive? Acceleration, remember, is the slope of velocity. It's the derivative of velocity. So what we want to look for here is, where is the slope positive? Well, the slope is only positive right here, from 3 to 5. Right? Everywhere else, it's either 0 or negative. So the acceleration is positive from 3 to 5 seconds, or again, we could write it in interval notation. All right, try number 4. How many times is the object's acceleration undefined? So remember, for a function to be differentiable, no corners, no cusps, no vertical tangents, no discontinuities. We have a couple of corners here, right? There's a corner right there actually, and right there. So there are 3 places where the derivative of velocity, which is acceleration, is undefined. It happens at 1 second, at 2 seconds, and at 3 seconds. It's kind of hard to tell here, but we can see that that slope changes. Right? That's not a smooth transition, so this is actually considered a corner. So 3 times, okay, would be the answer to number 4. All right, try this one. During 2 to 3 seconds, what is the object's acceleration? Well, acceleration is just slope of velocity, right? So I want to take a look at this piece and find the slope. So my coordinate points, all right, are 2, 0, and 3, -10. So finding this slope, right, I mean, I can just count boxes here, and if I go right 1 and down 10, my rise over run, I'd be going down 10 over 1, so -10 feet per second squared. All right. Try number 6. When is the object furthest to the right? This is actually an interesting question. Okay, if we think about velocity, whenever velocity is positive, that means we're moving to the right. So on this entire piece here, we're moving to the right. Then we stop, turn around, and move to the left on this entire piece because my velocity is negative. So the object is furthest to the right here, right? Because at this moment, I turn around and go to the left until the end, until 5 seconds. So it's furthest to the right at t equals 2. All right, try the last one. All right, average acceleration. Well, if we are given a velocity curve, we know acceleration is the derivative of velocity. It's the slope of velocity. So if I want average acceleration between 0 and 3, so here's 0 seconds, here is 3 seconds. What I want to do is just find the slope between those 2 points. Okay, I want to find the slope of this line. That will give me my average acceleration. So I've got the point 0, 5 and the point 3, negative 10. So the slope between these 2 points, I would be going down 15, right 3. So negative 15 over 3 equals negative 5 feet per second squared. So that is my average acceleration on this interval. All right. Last type of problem. Okay, we can think about these ideas in terms of a table. So here we're told this table shows the velocity at various times. We want to use this table to estimate the object's acceleration at 1.25 seconds. Well, we know acceleration is the derivative of velocity, right? To estimate the acceleration here, okay, 1.25 would obviously be in between 1 and 1.5 seconds. So what I can do is find the slope between these 2 values, and that will approximate the slope right in between them at 1.25. So what I can say is 12.2 minus 13.0 over 1 minus 1.5. So we get negative 0.8 over negative 0.5. All right. And I mean, we could actually do that division, and that comes out to a positive 1.6. So we would estimate that the acceleration at t equals 1.25 is 1.6 feet per second squared. Okay, and we did that by finding the slope between these 2 values here. All right, we're estimating the slope of the value right in between. So finally, you guys try number 9 here. All right, this one's really similar to the last one. The table shows the position at various times of an object moving along a horizontal line. If we're given position and we want to estimate velocity, well, I can again just use the slope or use the points on either side to estimate the slope right in between. So we can say 7 minus 10 over 3 minus 5. So that would be negative 3 over negative 2. Gives me positive 1.5. So if I'm estimating velocity, this would be feet per second. All right. And that will do it for today.